so in the next lecture we will be talking about determinants and inverses of matrices. So what is a determinant of a matrix? A determinant of matrix is a scalar that appears and this determinant appears in lot of problems, in several problems. For example, suppose you had a11 x plus a12 y plus a13 z equal to b1, a21 x plus a22 y plus a23 z equal to b2, a31 x plus a32 y plus a33 z equal to b3. Okay. So, suppose you had a system of equations. Okay. So we can write this as a times x equal to b, where x is basically this is x y z, b is b1 b2 b3, and a is this matrix. Okay, so this is a matrix. Okay, and Ax equal to b. Okay, so you can write these equations in this form. Okay, and now you can, to solve this, your goal is to solve this. So suppose you know a and b, you want to solve this for x. Okay, and you can solve this and you can show that when you solve this, you can write x as equal to the following. I will just write it, I will just write the answer. Okay. This is, so you write a determinant of a11, a12, a13, a21, a22, a23, a31, a32, a33. Okay. So this is just a determinant of a. Okay. And what you do in the, so this appears in the denominator. In the numerator, what you have is you have something like the determinant of a, but you replace the first column by b. So what you do is you replace the first column with the vector b1, b2, b3, and you take the determinant of that. Okay. Similarly, if you want to calculate for y, then you replace the second column of a with b1, b2, b3. Okay. So this is called as Cramer's rule. Okay. So you can do similarly for y and z. Okay. So I'll just write, you can do similarly for y and z. Okay. So basically you can solve this set of equations and determine x, y and z, and you can do this for an arbitrary sized matrix. Okay. You can do for arbitrary number of equations. Okay. So if you have more equations, you will have bigger matrices. Okay. So this is one place where determinants appear most naturally. Okay. And we also saw that determinants also appear in determinants are involved in calculating eigenvalues of a matrix. Okay. And we already saw that suppose you want to calculate an eigenvalue of a matrix A, okay, then you just take this matrix A minus lambda I and you set its determinant equal to 0. Okay. So this is referred to as the characteristic equation of A. Okay. So it is a characteristic, it is called the characteristic equation because the eigenvalues are often called, the eigenvalues refers to as the characteristic of A, and this is used to calculate eigenvalues. And we know that this leads to a polynomial equation in lambda. Okay. So determinants are very naturally involved in calculating eigenvalues of a matrix. Okay. Another place where the determinants are involved is in calculating the inverse of a matrix. So, in calculation of inverse of a matrix. Okay. So, suppose you had a square matrix A, okay, then we know that A times A inverse equal to identity, okay. And it turns out that you can express, you can write expression for A inverse using determinant of A and determinants of what are of various matrices involving various matrices which are obtained from A. Okay. So we can use various matrices that are obtained from A, and those determinants are also involved in calculating the inverse of A. Okay. So this is the next use of determinants, and just to illustrate, suppose you have a matrix A which has these terms A11, A12, A13 up to A1n, A21, A22 up to A2n, and AN1, AN2, AN3 up to ANn. So, suppose you have this matrix A. Okay. Now, you can determine what is the cofactor. Okay. So, the cofactors and minors of elements of A. Okay. So, for example, if you take Aij, or let me take a specific example. For example, if you take A23, okay. So this is an example, consider A23. Okay. Now, if you want to find the cofactor of A23 or the minor of A23, okay. So what you do, okay. So first let us say the minor of A23. So minor nothing but determinant of matrix obtained by eliminating. So what is done is you want to determine the cofactor of this element A23. Okay. So what you do is you make a matrix, you look at this matrix. Okay. So you look at this matrix where you have n minus 1 rows and n minus 1 columns. Okay. So one fewer row and one fewer column, and what you can say is that minor of A23 is nothing but determinant of this matrix A11, A12, then you eliminate the third column. So you have A14, A15 up to A1n, then you have you eliminated the second row. So you have A31, A32, A34, A35 up to A3n, all the way up to AN1, AN2, AN4, AN5, ANn. Okay. So this is what is meant by the minor of A23. Okay. And similarly, the cofactor, we have the minor determined of each element defined in this way. Okay. Now, there is something called a cofactor. So, cofactor of an element Aij, Aij is the element of A. Okay. This is nothing but minus 1 raised to I plus j times minor of Aij. So, you just take Aij and multiply it by plus or minus 1 depending on whether I plus j is odd or even. So, this is the cofactor of A. Okay. And what this allows you to do is two things. One is you can show that determinant of A is equal to A11 cofactor of cofactor of A11 plus A12 times cofactor of A12 and so on all the way up to A1n times cofactor of A1n. Okay. So you can expand the determinant in terms of cofactors. Okay. This is again you can easily verify this. Okay. And I chose you can do this using any row or any column. So you can also write this as A21 cofactor of A21 plus A22 times cofactor of A22 plus A2n times cofactor of A2n. Okay. So we can use any row or column to calculate determinants. Okay. So the minor of A is of any element of this of the matrix A is given in this way. Similarly, there is something called the cofactor which is defined based on the minor. So cofactor, again this is cofactor of an element. Let us say if you have A23, okay, this is minus 1 raised to 2 plus 3 times minor of A23. Okay. So this is basically this is minus 1 times minor of A23. In general, cofactor of Aij, okay. So we will use the notation capital A I j, okay. This corresponds to the cofactor of Aij. This is equal to minus 1 raised to I plus j times minor of Aij. So the cofactor of any element is minus 1 raised to I plus j times minor of Aij, and the cofactors are very useful because I can write determinant of A as A11 times cofactor of A11 plus A12 times cofactor of A12 plus so on A1n times cofactor of A1n. So I just take the elements of the first row and I multiply them by their cofactors and add all of them, and I will get the determinant of the A. I can similarly I can use some other row. I can use let us say A21 times cofactor of A21 plus A22 times cofactor of A22 plus all the way up to A2n times cofactor of A2n, or I can use any column. So we can use any row or column to calculate determinant. So these cofactors and minors are they play a role in calculation of determinants. Okay. They also play a role when you are calculating the inverse of a matrix. Okay. So we already saw that A inverse times A is the identity matrix, okay, and this is equal to A times A inverse. So this is the definition of the inverse. Now suppose you know the elements of A. Okay. So suppose your A is expressed in the usual way. Okay. Then you define a matrix of cofactors. Okay. So this I call it as I will just call it as cofactor of A of this matrix. This is a matrix whose elements are nothing but the cofactors of A. So this will be A11, A12 up to A1n, and then A21, A22. Notice it is capital A, which is a cofactor A2n, N1, An2 up to An. Okay. So instead of putting the element, you put the cofactor of that element. So instead of putting little a11, okay, I put capital A11, which is the cofactor of this is A11 equal to cofactor of A11. Okay. So this matrix of cofactors can be used to calculate the determinant. So A inverse is equal to cofactor of A divided by determinant of A. This is the matrix of cofactors divided by the determinant of A, which is nothing but the inverse of the matrix. So, you can calculate the matrix inverse, okay, and as I said cofactors, this is a matrix of cofactors. Okay. So, this is a matrix of cofactors, you divide that by the determinant which is a scalar. So, you will get a matrix, okay, and this is the expression for the inverse of a matrix. We have seen how to calculate inverse of a matrix and what are the uses of determinants. Okay. Now, let me briefly mention a few properties of determinants that are of interest. So, determinants, okay, since these appear very often. Okay. So, some properties of determinants that are of interest is that they are unchanged when rows and columns are swapped. That is, in other words, determinant of A equal to determinant of A transpose of the transpose matrix. Okay. They change sign on swapping any two rows or columns. If you interchange any two rows or any two columns, okay, then the determinant will change sign, it will become negative of that. Okay. The other thing, other two important points are that they remain unchanged on cyclic permutation of rows or columns. If I shift all the rows or columns to the right. So, for example, if I take this matrix, okay, and let us say this is A11, A12 up to A1n, A21, A22 up to A2n and so on. And I take this matrix and then I do I sort of shift everything to the right by 1. So, what I do is I put A11 here, A1 n minus 1, okay, and I take A n and I put it here, A n 1 and I put or A 1 n and I put it here. So, what I did is I shifted everything to the right by 1. So, you shift everything to the right by 1, okay, and you do this for all the columns. So, this will be A 2 n, A 2 1, A 2 2, A 2 n minus 1, A n n, A n 1, A n 2. So, now when you do this cyclic permutation, okay, of rows or columns, then the determinant is unchanged. So, determinant of this matrix equal to determinant of A. So, a determinant remains unchanged on cyclic permutation of rows. You can do that for columns also. Okay. The next probably another very important use of determinants is that determinant equal to 0 if two rows or columns are identical. Okay. So, if any two rows or any two columns are identical, then the determinant is 0. Of course, if any row or column, if any row or column has all elements equal to 0. Okay. So, if any row or column has all the elements equal to 0, then the determinant is unchanged, is equal to 0. Okay. And so what this implies is that determinant of let us say you consider you do something like this. So, you have A11, A12 up to A1n. Okay. Then instead of A21, you do something like A21 minus alpha A11, A22 minus alpha A12, A2n minus alpha A1n, and you take the and you leave again you leave the rest of them the same, A31, A32 up to A3n, AN1, AN2 up to ANn, okay. And you take the determinant of this matrix. So, this is equal to determinant of A. Okay. Now, what did you do here? You took the second row, okay, and you subtracted alpha times the first row. Okay. So, so you did a row operation, what is called an elementary row operation, and you found that this leaves determinant unchanged. Okay. So, this is again a very important idea, okay, that if you take a matrix, you do an elementary row, you can do an elementary column operation also, you can do for any row or any column. Okay. If you do these operations, then the determinant is unchanged. Okay. So, now these are some of the important properties of determinants that make them very useful in various applications. Okay. So, I will conclude this lecture here, and in the next class we will try to do some practice problems involving all these concepts.